Welcome to the deep dive. Today, we're tackling a challenge, one that pretty much every network architect faces sooner or later. How do you grow your network? How do you stretch it across different physical places, maybe connecting remote offices, maybe scaling out in the cloud? And how do you do all that without hitting performance walls, creating security holes, or just ending up with a completely tangled mess? The pressure on networks is just relentless these days. So we're going deep on a technology that's really changing the game for modern data centers, for cloud environments, VXLAN, that's virtual extensible LAN. Think of this as your shortcut to getting your head around not just what it is, but maybe more importantly, why it matters and how it works in the real world.
And we're not just scratching the surface here. Our focus today is very specific. It's how VXLAN is implemented on Ruckin ICX fast iron switches. We're talking models like the 7550, 7650, and 7850. The idea is to give you practical stuff, things you can actually use when you're designing networks.
Okay, sounds good. Let's unpack this then. Let's see how VXLAN can genuinely shake up your network architecture. So starting right at the core, VXLAN is a tunneling protocol. I often try to explain it with an analogy like, imagine you're creating this dedicated, super fast express lane just for your company's traffic. But this express lane, it's built right over the regular public highway like the internet. Can you elaborate a bit? What's it extending and over what?
That's a great way to put it. Basically, VXLAN lets you stretch your Layer 2 networks, think traditional VLANs, across Layer 3 infrastructure. The clever part is, the underlying Layer 3 network, your normal routed network, it just sees the VXLAN traffic as regular data packets. It doesn't need to understand the Layer 2 stuff inside. It effectively acts as a transparent transport, so you can have what feels like one big local network, even if your servers are, miles apart or in different data centers entirely.
Right. That immediately sounds like a huge step up from where we were with standard VLANs. What was the big push behind developing it? Was it really just about running out of VLAN IDs?
That's definitely a major piece of it, yeah. I mean, think about a modern cloud provider or even just a large company with lots of departments needing isolation. How many separate networks did they need? Traditional VLANs use a 12-bit ID. That gives you, just over 4,000 possibilities? 4096 technically. In today's world, with massive virtualization and multi-tenancy, that's just not enough. It became a real bottleneck.
Okay, so scale was a huge driver.
Exactly. And that brings us to the aha moment for VXLAN. The VNI, that's the VXLAN network identifier. Instead of 12 bits, the VNI is 24 bits long.
24 bits. Okay, that sounds like a lot more.
It is. It means you can have potentially 16 million distinct logical network segments. Compare that to the 4,000 VLANs. It's not just an increase. It's a completely different scale. It gives architects enormous freedom to segment networks for security, for tenants, whatever they need, without worrying about running out of IDs.
16 million. Wow. Okay, that number definitely changes the game. But how does it actually do that trick? Layer 2 over layer 3. I've heard it called a Russian doll structure. Can you unpack that encapsulation?
Yeah, the Russian doll analogy works really well. So you start with your original data, the inner Ethernet frame. That's the smallest doll. VXLAN then wraps that frame in a VXLAN header. This header contains that all-important VNI telling everyone which logical network this packet belongs to. Then on top of that, you get a standard UDP header. Then an outer IP header. This is what the Layer 3 network uses for routing. And finally, an outer Ethernet header for the physical transport.
So the underlying network just sees a standard UDP IP packet.
Precisely. It routes it like any other UDP packet across the physical network. It has no idea there's a whole Layer 2 frame hidden inside. That's what makes the Layer 3 network a transparent underlay for all these Layer 2 overlay networks. It's incredibly flexible.
And the devices doing this wrapping and unwrapping, the entry and exit points for this VXLAN tunnel.
Those are your VTEX virtual tunnel endpoints. These are the devices like the Ruckus ICX switches we're focusing on that actually perform the encapsulation when traffic leaves a VXLAN segment and the decapsulation when it arrives. Think of them as the on-ramps and off-ramps for your VXLAN superhighway.
Okay, that scalability and mechanism makes sense. But, standards are one thing, implementation is another. Every vendor does things slightly differently. For someone using REQ's ICX switches, what are the unique bits, the distinguishing features they really need to be aware of?
That's a crucial point. One key difference in the REQ's fast iron implementation, specifically on the ICX 7550, 7650, and 7850, is how it handles BUM traffic. That's broadcast, unknown unicast, and multicast traffic. Stuff that needs to go everywhere, or at least to multiple places within the segment. Now, the standard RFC 7348 generally suggests using multicast in the underlying Layer 3 network to handle BUM efficiently. However, Rucky's fast iron uses something called static ingress replication.
Static ingress replication. Okay, what does that mean in practice? How does it differ from using multicast?
It means that when a VTEP needs to send out a BUM packet, instead of sending one copy to a multicast group address, it actually creates multiple copies of the packet. It then sends one copy directly to every single other VTEP that's part of that same VXLAN segment, that same VNI.
Ah, so it replicates the packet at the source VTEP and sends unicast copies to all the peers.
Exactly. This does mean you need to explicitly configure all the peer VTEPs on each switch. You need that full mesh of information for it to work for VLAN extension. The trade-off is that it simplifies the underlying Layer 3 network. You don't need to set up and manage multicast routing in your underlay, which, can sometimes add complexity.
Right, simplifies the underlay transport, but requires more explicit configuration on the VTEPs themselves.
Got it. That's a really important detail for deployment. What about flexibility features?
Ruckus ICX definitely offers some nice flexibility. One thing is multiplexing. You can carry traffic from multiple different VNIs, multiple logical networks over a single VXLAN tunnel. That's efficient. But I think the real standout for many users is VLAN translation. This is super useful.
VLAN translation. How does that work? Okay, imagine you've got VLAN 100 doing a specific job on a switch in your main office. Then maybe you acquire another company, or you have a remote site, and they use VLAN 200 for the exact same purpose. Normally, bridging those would be tricky, but with VXLAN on Ruckus, you can map both VLAN 100 on the first switch and VLAN 200 on the second switch to the same VNI. Poof. They become part of the same logical Layer 2 network, even though their local VLAN tags are different. It's fantastic for integrating networks, handling mergers, or just sorting out VLID overlaps without needing to re-IP everything.
That sounds incredibly useful, especially in messy real-world scenarios. And you mentioned VXLAN gateways earlier. What's their specific role?
Right. The VXLAN gateways are key for connecting your VXLAN world to the non-VXLAN world. They act as the bridge. They allow devices within a VXLAN segment to communicate with devices on traditional VLANs or routed networks, and vice versa. They essentially support these full mesh ELAN services, connecting everything together.
Makes sense. Are there any specific limitations or configuration details on Ruckus ICX we should flag?
Yes, a few important ones to keep in mind. Generally, the system supports only one overlay gateway instance per switch. Also, while you can map ranges of VLANs, the typical configuration enforces a one-to-one mapping between a local VLAN and a VNI. Oh, and you can't map the default VLAN 1. And here's a really critical practical point, something that catches people out. That VXLAN encapsulation. It adds overhead. About 50 bytes get added to the original Ethernet frame.
Ah, the MTU trap. 50 bytes. That's not insignificant. So you're saying the maximum transmission unit on the network links between the VTEPs needs to be higher.
Absolutely. Your transport network MTU must be configured to handle this larger frame size. You need at least the standard 1500 bytes, plus maybe some overhead, plus those 50 VXLAN bytes. So you're looking at configuring an MTU of, say, 1600 bytes or even higher on all the links in the underlay path. If you don't, those larger VXLAN packets will just get dropped, fragmented, or rejected, and you'll have connectivity issues that are sometimes really hard to track down.
Classic network troubleshooting headache right there. Anything else?
One more for now. Currently, when you're defining those remote VTEP sites, only IPv4 addressing is supported for the remote peer IPs.
Okay, good to know. So we've got the concepts, the Ruckus specifics. Now let's get practical. For the engineer who needs to actually set this up on an ICX switch, what's the basic workflow? Can you walk us through the essential configuration steps?
Sure, it's pretty logical. Step one is usually creating the VXLAN gateway itself on the switch. This is sort of the main process controlling VXLAN operations on that device. Step two is the mapping. This is where you link your local VLANs to specific VNIs. You're basically saying traffic on this VLAN belongs to this extended VXLAN network. And remember, no mapping the default VLAN.
Okay, create the gateway, map VLANs to VNIs. What's next?
Step three is defining the remote sites, your peer VTEPs. You need to tell the switch the IP addresses of the other switches participating in the VXLAN fabric. And Ruckus gives you redundancy here. You can configure one primary remote IP address and then up to 15 secondary IPs for each peer.
15 secondaries? That sounds robust. So if the primary path or VTEP fails?
Exactly. That leads to step four, enabling failure detection. You configure keep alive messages, usually simple ICMP pings, that constantly check if the primary remote VTEP is reachable. If those keep alives fail, the switch automatically starts using one of the configured secondary IP addresses. It's like having backup routes programmed into your GPS, ensuring the tunnel stays up if there's a problem.
Makes sense. Automatic failover. And the final step.
The final core step is extending your VLANs to those remote sites. You basically tell the gateway which of your mapped VLANs should actually be active across the tunnel to specific remote peers. Once you do these steps, you've laid the foundation for extending those layer 2 domains.
Great, that covers setup. Now, inevitably, things sometimes go wrong, or you just need to check if things are working as expected. What are the essential commands for monitoring and maybe troubleshooting VXLAN on Ruckus?
Yeah, for day-to-day checks and troubleshooting, there are a few go-to commands. Show Overlay Gateway is your first stop. It gives you the overall status, configuration details, VNI mappings, everything. To check Layer 2 connectivity across the tunnel, you'll want to see the MAC addresses learned from the remote VTEPIs. The command for that is show MAC address VNR site. And if you're digging into a performance issue or you've made changes and want to reset the counters, clear Overlay Gateway VNID counters is very helpful. You can clear counters per VNI.
Being able to see MACs learned remotely seems crucial for verifying it's actually working end-to-end.
It absolutely is. And beyond those specific commands, getting statistics per VNI or even per interface involved in the VXLAN tunnel is really valuable. It lets you pinpoint where traffic is flowing or where potential bottlenecks might be forming within specific logical networks.
Okay, so we've built a solid foundation. Basics, Ruckus specifics like static replication, config, monitoring. But modern networks demand more, right? What advanced features does VXLAN on Ruckus ICX bring to the table for building, say, more robust or more secure setups?
All right, but moving beyond just simple layer 2 extension, we get into some powerful capabilities. One major one is VXLAN Riot. That stands for Routing in and Out of Tunnels.
Riot, routing inside the tunnels. What does that allow?
Exactly. It enables layer 3 routing between different VXLAN segments, VNIs, directly on the VTIP switch itself. So instead of traffic having to leave the VXLAN fabric, go to an external router, and then come back into a different VXLAN segment, the routing happens right there on the switch handling the tunnel endpoint. It's much more efficient for inter-VNI communication.
So distributed layer 3 routing within the overlay. That sounds like a big deal for things like microsegmentation, keeping traffic localized. Which switches support Riot, and are there any catches?
It is a big deal. It's currently supported on the ICX 7550 and 7850 models. There are a couple of key things to know, though. First, Riot is disabled by default, and it only supports unicast routing between VNIs. Second, and this is important, enabling Riot requires a system reload. And critically, it involves repartitioning the hardware forwarding tables on the switch. You're essentially dedicating some hardware resources specifically for this overlay routing, which means it can potentially impact the total number of layer 3 routes the switch can handle for the traditional underlay network.
Okay, so there's a trade-off. You gain efficient inter-VNI routing, but you might reduce your overall layer 3 scale, and it needs a reload and careful planning around hardware resources.
Got it. Now, let's talk security. VXLAN is great for connectivity, but the tunnel itself isn't inherently encrypted, right? If you're sending sensitive data.
Correct. Standard VXLAN just tunnels the layer 2 traffic. It doesn't secure it within the tunnel. That's where MACsec over VXLAN comes in.
A MACsec over VXLAN. So, encrypting the traffic inside the tunnel. Precisely. MACsec provides strong hop-by-hop encryption at layer 2. By applying it to the VXLAN tunnel traffic, you get end-to-end encryption for the original layer 2 frames as they travel across the layer 3 underlay. This is crucial if you need to protect sensitive data traversing your LAN, or especially across a WAN link using VXLAN.
That sounds like a very robust security posture. Is setting up MACsec over VXLAN straightforward, or is it complex?
It has some very specific requirements. You typically need dedicated VLANs just for the MACsec traffic. You configure loopback ports for the MACsec session to establish. And interestingly, MAC learning is usually disabled on the physical MACsec port itself. So yes, it's a specific configuration, but it provides that strong point-to-point layer 2 encryption within the VXLAN overlay.
Dedicated VLANs, loopbacks, MAC learning disabled.
Okay.
Specific but powerful. One more area, quality of service. How does VXLAN handle prioritizing important traffic?
Good question. Ruckus ICX handles QoS quite elegantly for VXLAN. It ensures that the priority markings on the original tenant traffic are preserved. Basically, the DSCP value from the inner IP header, if present, and the layer 2 EOS, class of service, priority value from the inner Ethernet header, are copied to the outer IP and Ethernet headers that are added during VXLAN encapsulation. This means your existing QoS policies that classify and prioritize traffic based on those markings will continue to work seamlessly across the layer 3 transport network. Critical applications still get the priority they need.
That's clever. Copying the QoS markings ensures end-to-end priority. Okay, wow. We've covered a lot of ground here. From the basics of layer 2 extension to Arfexa specifics like static replication and VLAN translation, configuration, monitoring, and these advanced features like Riot and MaxSec. It really seems VXLAN on Ruckus ICX is a seriously powerful toolkit. That scalability, the security options, the flexibility, it really enables abstracting the logical network from the physical.
It really does. I think the key takeaway for anyone listening is to consider how this ability to decouple your Layer 2 logical networks from the underlying Layer 3 physical infrastructure can solve your specific network challenges. Whether it's scaling data centers, connecting campuses, enabling multi-tenancy securely, or just simplifying network integration, VXLAN offers a level of agility that just wasn't feasible before. It opens up a lot of architectural possibilities.
Definitely food for thought. If you found this deep dive helpful, maybe share it with your colleagues and, keep exploring these technologies that are constantly reshaping how we build and manage networks. And maybe a final thought to leave you with. Reflecting on those RQ specifics, the static ingress replication, the hardware partitioning trade-offs with VXLAN Riot, the specific setup for MaxSec over VXLAN,
Mhm.
how might understanding these nuances allow you to design networks that are not just functional, but significantly more resilient, agile, and secure than you might have initially thought possible with just a generic understanding of VXLAN?